curve for a ferromagnetic material, and you observe it's non-linear because after certain value of the flux density B start to saturate. So to be non-linear after the knee of the curve. However, for air, never saturate, just straight line. But if we are working in this region, we can approximate the curve to a linear relationship or a straight line, as you see, and then from this straight line you can find the permeability of the material itself. So it depends which region you are working on. That's acceptable to approximate it if you are working from 0 up to, let's say, 1 Tesla, for example. There is an important phenomena in magnetic circuits, which is called hysteresis. I wonder if you had this in physics before. Okay. If we have a toroid or ring, and we wrap coil with the number of turns equal n, and we apply sinusoidal current. Why we want to apply sinusoidal current? See, we want to test what's happening if the current in the coil start from 0 increasing, reach value, then go back again decreasing, reach zero value, then positive will be negative. So I want to see what's happening inside this material. So in the beginning, let's just take this curve, make it bigger a little bit. When we start from 0 and we're increasing the current, when we increase the current, we increase the field intensity H. Because as you know, there is a relationship between field intensity, H, and current. Do you remember what's the relationship between H and I? Which law that controls the relationship between the field intensity and the current? Ampere's. Let me just refresh your memory. Ampere's law said that simply sigma HL equal NI. So, and L is closed path, that we did that. So there's a relationship between current and H, because if we say L is fixed, in this example, that's our L. That's the mean path inside this ring, and we can calculate that. There is one problem, I think, in the notes. If you know the inner radius and the outer one, then you can average them, and then you can get the average radius, and then you can get the circumference of this path. That's the length that where the magnetic flux flow. So let's just go back. So there is a relationship between H and I. Every time you increase I, you increase H. So that's how you control H, just by increasing I. So increasing the current, according to the sinusoidal curve here, the current is increasing from 0 up to the maximum value I max. So what will happen? It will increase, B will increase, the field density will increase when the field intensity increase, or flux density B will increase when the current increase gradually. And if you increase more, it will reach saturation, because we are doing this test on a ferromagnetic material. So it will reach saturation. So if you continue increasing the current, it will just be like a straight line in saturation. But we're doing sinusoidal, and then when it reaches the maximum, when it reaches the maximum value, then start to decrease. By the way, this point maybe is not corresponding to the maximum current here. Maybe it's corresponding to here, but the current still increasing. This one saturated. Then it reached the maximum value, then it start to decrease. The current start to decrease. What we observe that it will not go back on the same line. When decrease is supposed to go back, but it doesn't. Instead, it will go a little bit above the other straight line. And when it reaches zero here, it will the field density will not be zero. Something left. So if you have a ferromagnetic material and you have coil wrapped around this material, and you want to make it like electromagnet with the current, and what's happened if you disconnect the current, you think you don't have any magnetic effect in this core or this iron core. No, there's some left. So this value, we call it BR, the residue. That's the residual flux density left. Physically, as we explained last time, there are kind of small magnets inside the material. We call it the domains. So when we reverse, not all the domains go back again to be equal zero. Some left, some left. Okay. And if you continue decreasing the current, now the current will turn to negative. So it will come at this point. At this point, the current equal to zero, right? The value, that's a negative value of the current, a negative value field intensity. But let's say again, when we decrease the current, reach zero, we didn't get rid of all the magnetic effect or the magnetism inside this core. Something left. If you continue to decrease the current at certain negative value of the current, so you need this value of current or this value of field intensity to clean the core from the old magnetism inside. We call this HC. This is force. This is the force required to bring all the domains inside the ferromagnetic material to zero. No magnetism inside. We call it HC. You can continue the experiment by decreasing and increasing again. It will be repeated the same phenomena. We call this hysteresis. So since we start from zero and we never go back to the same value zero, whenever you will be just inside this loop. So there is some kind of energy lost. And we call this hysteresis loss. It will be existing in transformers and all electric machines due to the physical phenomena inside the ferromagnetic material. And if you change the value of the sinusoidal current, if you make it smaller, for example, you get another loop inside. So all these loops that you can see, they are corresponding to different values of current or different values of field intensity. So that's the physics of the hysteresis or what's happening inside the ferromagnetic material.
So here you will never be able.
Again to zero, yeah. That's why we say it has loss called hysteresis loss. There is another phenomenon. We have magnetic field, as you see here. And we have any piece of metal, iron, rubber, whatever. When you have this piece of metal, and if this magnetic field is changing with time, how can we get magnetic field changing with time? Right? Yeah. If you have a coil, if you have a fixed current, you have fixed magnetic field. You have variable current, you have variable magnetic field. Why? Because as I said, according to Ampere's law, the field intensity H is proportional to the current. So let's say this current, that's why you see the coil, we have sinusoid, something is changing. So we'll have sinusoidal magnetic field lines. So what's happening here, the magnetic field line is changing. What happened? Induced voltage. According to Faraday's law in physics, if you remember, have like a magnet and we have a conductor, and if we move the conductor or to move the magnet, we'll find that there is current flowing in this. If you close the circuit, it's current. That's called Faraday. So there is induced EMF when there is relative out. So that's Faraday. That's north and that's south. We have magnetic field fixed, not changing with time. And you have a conductor. This conductor, let's say, connected to something that can measure any voltage. So if you leave the conductor not moving and the magnet not moving, nothing will happen in the galvanometer, just will be at zero. Zero EMF is produced. If you move the conductor, shake the conductor, then you will find the galvanometer or whatever measuring instrument you're using will detect induced EMF voltage. And if it's closed, then the current will go through this loop. If you let the conductor at its place stationary and you move this magnet, you will find also that you will have deflection in the measuring instrument, which means there is an induced EMF in the circuit. So you got to have relative motion. So what will happen here in this diagram or this experiment, we fix the coil, we fix the plate, because maybe somebody think maybe you are shaking the conductor, maybe you are shaking the measuring instrument. So okay, we'll do this experiment. We'll have the coil and we'll apply sinusoidal voltage. So we'll have sinusoidal current. So sinusoidal field, magnetic field, it will be intersecting or linking with this metal, piece of metal. So what will happen? According to Faraday, some kind of EMF will be produced in this piece of metal. Yes. And since this piece or the plate is like solid surface, so an EMF produced, so it's like you have small circuit inside. So you will see, as you see here, circles. These circles all currents. Shape of the magnetic field itself. So these currents, like in circles, that's why we call it eddy currents. We call it eddy currents, and that's a very important phenomena. It happens in transformers, it happens in electric machines, and also it causes power loss, energy loss. And that's why I observed that when we adapter and if you have an adapter or charger that has transformer, the one that we have now doesn't have transformer, but if you have any equipment or device that has transformer and you plug it in the wall and you don't use it, it gets hot. Because the magnetic field reduced, you don't have to it have the eddy current and then you got the loss. So it produces heat, that means there is a loss because of eddy current. So how the can solve this problem? Because every machine transformer, you have cool and magnetic field always will apply sinusoidal and always have this problem. So if you want to solve this problem, what you will do? But at least, let's say, how you minimize the value of the current. This problem, you are an engineer and tell you, okay, we have this problem, we have eddy current, the current is big, it's causing heat, we are losing energy for nothing, and we want to minimize it. Yeah. Adding dielectric means that it's isolating, so you will lose some characteristic of the material because you want this material. If you have, for example, if you have transformer, you have a core, you need this core made of iron. So if you put dielectric, so you'll not have strong magnetic field. So you minimize the magnetic field. Problem is the value of the current is really high because it's a block metal. You know the resistance for electric current, it's equal L over A, and then you can say the resistivity. So now, you cannot change anything about resistivity. It depends on the type of the metals. You can't change anything. But how can you reduce the resistance? So what happened? Instead of having block of the iron, this block, for example, make it sheets. And these sheets, take them together, but put like insulation material between every sheet and the other one. 100 sheet, 10. When you make it 10, then you start, because this block is nothing. Make it sheet, the area is very thin, and the resistance is very high. That's why when you look at any transformer, find sheets and stick to each other. But there's a thin insulation material between each plate and the other one. That's why they do it. Lamination of the core. That's what we call it. So that's how we reduce the eddy current. When we will study transformer machine, you will observe that we add both losses, hysteresis loss and eddy current loss, and we call it core loss, because all this loss inside the core, right? And we call it PC. P power, C the core loss that we are going to use in the. You have any question about these two phenomena? That will be the last section in the magnetic circuit, and then after that, hopefully finish that today. Then we'll start next lecture, transform. All these are the basic concepts that help us to understand electric machine. I know that should be done in physics, and I'm sure done in physics, but I want to make sure that you understand the concept. Again, Faraday law, well, that's something that we used a lot, especially when we are working with transformer generators motor. That's I will make just a quick review. You have a coil wrapped about core or air, doesn't matter, and then you have a magnet. So what's happening if you are moving? I just explained that a few seconds ago. So if you move the magnet forward or backward, we observe that there's induced EMF in this coil. So what's happening? What's happening that, as we said, in our universe while living, everything reacting in the same way, but under different variable names, but the same thing. So what's happening when you are moving the magnets or the coil, the number of flux, of magnetic lines that they are going towards the coil increasing. So what's happening? The coil, the part inside, do you want to resist this? So what do? You reduce EMF, because EMF is like voltage, and by the way, it's voltage kind of potential energy. Because if you think about even mechanical engineers, they have potential energy. In electricity, we have potential energy. And both are the same. It means the position of electrons from the atom and the potential energy, if the height, the same. So what's happening? They arrange themselves in a way to increase the potential energy in a specific direction. I will talk about it just in 1 second. And in a way that the current, when you close the circuit, the current produced in this coil will make magnetic field opposing this. It will produce something to make it again back to 10 to 8 as a resistance, as a reaction. So EMF is equal d phi by dt, the rate of change. As fast as it's changing, the EMF is higher. Somebody pushing you gently, you are resisting gently. If pushing you fast, you will react fast, right? It's normal. So d phi by dt, the rate of change in magnetic flux. Increase, the EMF increase. And also proportional to the number of turns, because every turn is doing action. So it's n d phi by t. Why you put the negative? What direction? What I said, that this is explained by Lenz's law, because the current direction, it's in a way to build magnetic field opposing what's happening. So if the magnetic field going towards this ring, the current will go in a way to make magnetic field opposing, because it's coming attacking it. If you are getting this away from the ring, from this coil, so what's happening? The number of magnetic field lines decreasing. So they don't want that. So they reverse the direction of the, make magnetic field lines substituting what's missing. This universe, the same thing, same reaction, magnetic field, electric field. So that's why I put the negative, because the direction of the current will oppose whatever happening. If the number of lines, magnetic field increasing, it will make it to decrease in direction to decrease. If it was decreasing, it will make it a way to increase. That's why the negative. So when we do the analysis, we don't have to put the negative, but this is the meaning of the negative. That's Lenz's law. Okay. I know also that you studied in circuits inductance. But first of all, do you have any question about the Faraday's law and Lenz's law? You had this in physics, right? The current produced by the coil is producing magnetic field action of the main magnetic field, the change in magnetic field. Like magnetic field coming to, they are increasing, so to make current in the direction to make opposing magnetic field to this increase, to decrease. If it was decreasing, it will make it to assist, substitute whatever missing. It's a reaction. Inductance, that we call it L. Let's just go through it. That's the induced EMF by removing the negative sign, because the negative sign, just as explained, that's the meaning of the negative sign. So let's look at the magnitude of the EMF. It depends on n d phi by dt. All right. How you find d phi by dt? You will say d phi by di, di by dt. It's the same thing, right? And the d phi by di, the change of magnetic flux with respect to current, that's what we call it the inductance. So the inductance is the rate of change of flux with respect to current. If you have a linear L, you can say L, you can make it approximate it as delta phi by delta I. Increase the current, how much flux increase, that depends on the inductance of the material. So that's the definition of the inductance of material, the rate of change of flux with respect to the current. All right. So yeah.
So why is
I just said, because negative sign, it means it's the reaction for the magnetic field. Now we are interested only in the magnitude.
oh, okay.
Yeah. So that's the definition of the inductance. If we continue, so if L is equal d phi by dt, but actually if we have the N, so we can put this one inside to make it completely for the all terms in the coil. So N d phi by. So that's the definition of the inductance. And as you know that we called lambda N phi. What does it mean? Every single coil or every single turn in the coil, there is magnetic flux linking with it. So you want to find the total flux linking to the whole coil with the all turns. If you have one turn, you will have 1 phi. If you have 2 10, you have phi, and phi 2 phi, 3 phi. So that's the total. So lambda is the linking flux, or the flux linking with the whole turns of the coil. So that's the definition of the inductance. So you can approximate it by this way. just remember, it's just flux per current. Let's, if you wanted to design the L, if you want to make L, whatever, 3 Henry, 4 Henry, 10 Henry, so how do you do that? That's the definition of L, and we are going to find the dimension of L that's affecting. So from Ampere's law, we just reviewed HL equal NI. Okay, so that's HL is equal NI. If you want to differentiate DH by I, so what you get, or say DH, L is constant, will be outside the equal, N is constant, and I can be changed. So if you have DH divided by DI, it'll be equal N over L. So that's DH by DI. Okay. That's L. We start from the flux link, lambda is equal N phi. What's the flux? It's equal flux density times the area. That flux is equal flux density times the area. So that's the flux link. So lambda in the end, instead of N phi, N BA. Okay. What's the relation between B and H? B is equal mu H. So I replace B by mu H. So you have N and B replaced by mu H, and that's A. So that's flux linking. Because you have to remember there are two fluxes, flux linking and flux linkage. There are two things. Let me just remind you what the difference between both. If you have coil, because it will use it in transformer. If you have coil, and this coil applied by electric current, it will have magnetic field everywhere, but there are sets of magnetic field linking with the second coil. That's the first coil, second, that's linking flux. But the one is not linking, is not useful. We're losing it. That's the leakage. Because of that leakage flux. So it's important for us, the linking one, the one linking both coils. So here we have lambda N mu HA, come from there. Okay. And we know that L is equal D lambda by DI, and I will remind you, lambda is equal N phi. So let's differentiate with respect to I. We know lambda from this equation, we'll substitute by lambda here, so it's equal N mu HA, and then we'll start to differentiate with the current. N is constant, number of terms. Mu, permeability, it's a fixed number. H, variable. Area, cross-section area, doesn't change. So you get N mu A all outside the differentiation, and what's left only DH by DI. So L is equal N mu A, the differentiation of H with respect to current. That's why here I tried to find DH by DI, so I went back to Ampere's law to find DH by DI, and I found equal N divided by L. So I replace this by M divided by L. I will have N mu A, and I found DH by DI is equal M over L. N times N is equal N squared mu A over L. So we got the equation that will help us to design any inductance. So if you want to make inductance 5 Henry, you have the equation here. You have the number of turns, mu, it's the permeability of the core. It means if you want to have inductance wrapped around ferromagnetic material, it's mu. If you want to just make like a cylinder and there is air, so use mu naught. Whatever the material, of course, will be better if you use ferromagnetic material. Will mu. A, the cross-section area. L is the length. So it's in your hand now, L. If you say I want to make 10 millihenry, so that's the equation that you have. You design. L is the length. That's the length. If you want to make it like in a core, that's your length here. The coil number, the number of turns, that's N. You don't need the value of the current, by the way. Inductance now, it's just you know the dimension of the inductance you're going to design. You know the length, that where the magnetic field will go through. You know the permeability of the core, the cross-section area. That's in your hand, you design. So now we can do the inductance. And as so now we just prove that. Let me go back and see the main equation we got here. We have equal L di by dt. Because we have E, originally E is equal. If we remove the negative sign, that's the general form. Is the change of flux with respect to time. Remember, flux linking N phi. If you have only one term, it will be reduced N equal 1. In this case, you will say E is equal N, I'm sorry, d phi by dt only, if you have N equal 1. If you don't have N equal 1, it will be N d phi by dt. But you know N phi is equal number, so you can, this is general form. But the negative sign just will, it will give the physical meaning that I explained. This is the magnitude. And we know that what's the relationship between lambda and L? You know that L is equal what? That's L that way, just the first N d phi by dt, or as we explained, d lambda by di. That's L. From these two equations, you can say E equal d lambda. You want to say by dt, okay, put di here and di. That will be equal to L times di by dt. And that's the equation you have it in circuit 2. The voltage across the inductor is equal L times di by dt. All right. There is an equation here. An example. We have magnetic circuit. And this magnetic circuit, you have the air gap equal 1 millimeter. LC is equal 50 centimeter. The area, the cross-section area of the core equal the cross-section area of the air gap is equal 15 centimeters squared. And the relative permeability for the core is equal to 3000. The current is equal 1 ampere. What's required here? Find flux density in the air gap and the inductance of the coil. So we want to find the flux density in the air gap, and we want to find L. This has L. Inductance. Can we have air gap? Yes, you can have air gap. Yes. And that's the equivalent circuit. I will let you solve this now. Every 2 or 3, try to solve it together. No, I'm not telling that's all. Only who give the right answer, both answers will get the bonus. That's all. But question, how to find flux density? Find flux density B. B. To find B, what's supposed to get? You have to have phi, right? Because the flux density equal phi over area. So you need the flux density in the air gap and the area gap. You have the air gap, so you have to find the flux density. How you find the flux itself? What's the relationship? What do you have, and how can you find the flux? Do you know any equation that relate flux by current, by L, by all the information given in this problem? What is the relationship? The the MMF, magnetomotive force F, which is equal NI, it's equal what? That's like voltage, equal the reluctance. That's the equation will help you to get the So you start from what? Start from the reluctance of the everything. Then when you find the reluctance, you have N, you have I. Then you get, that's the first thing you get. Second thing, third. Then you got the first requirement. Find the reluctance. Then you find the flux. Then you find the flux density. Okay, N equal 400 turns. Equivalent circuit will help you to find phi. You have to find RC, the pool, and then Yes. 0.5. We're asking about the current. So if you look at the equivalent circuit, like in I like voltage. So I by the total reduction, then you get Find L. Observe what we got here, L. That's when you design it, and that's when you have a relationship between the parameters. If you can have lambda and I, or you can have n square over the reluctance. Yeah. So and the inductance of the whole system.
We
Yeah, it's yeah, 258 million. Yes. That's L. 258 million.
Oh yeah. Yeah. Oh yeah.
Yes. Yeah.
So I was wondering, is the bonus something you're supposed to
Using what?
Is it the bonus? Like.
Yeah, but you guys exceed the time.
Oh.
Just,
We're actually done before.
not only you, everybody. It took it's a bit 5 minutes, but it took a long time.
Thank you.
5 minutes will be yeah.
One of the slides you did was the one with the mysterious stuff. Does it call mysterious?
Hysteresis.
Hysteresis. You did